So if we look at a molecule and we can determine its ability to hydrogen bond with water, we can know something about its solubility. Before we move on, I just want to mention something about gases. And this is going to be important when we look at hemoglobin and myoglobin. So gases that are nonpolar, which is things like oxygen, O2, and nitrogen, N2, those gases are nonpolar, and because they're nonpolar, there's no potential for them to hydrogen bond with water, and so they are relatively insoluble in water. But when we look at other gases, for example, ammonia, can I draw this? I'm going to try. So here's ammonia, and you know that nitrogen usually has 3 covalent bonds to other atoms, and then it has a lone non-bonding pair of electrons. Because ammonia has this non-bonding electron pair, it has the ability to form a hydrogen bond with water, and so we have the potential to form a hydrogen bond here. This nitrogen hydrogen bond itself is polar, so we can then form a hydrogen bond with water over here. These are the non-bonding electrons on the oxygen, and we can form a hydrogen bond dot dot dot. That's my hydrogen bond. It's the dots of the hydrogen bond, and we can form a hydrogen bond across here, right? So ammonia is pretty darn soluble in water because it has the potential to hydrogen bond with water. We're looking at some molecules here that are examples, and this should help you with the homework assignment for the weekend. So over here we have glucose, and when we look at the structure of glucose, we should look for clues for ability to hydrogen bond with water. And so the first thing that we're looking for here are non-bonding lone pairs of electrons. So we have a non-bonding pair of electrons here and here on that oxygen in the ring. We have electron pairs here on this oxygen, right? And here, you get the picture, right? Wherever we have a non-bonding pair of electrons, we have the ability to form a hydrogen bond with water. And so I'm drawing a water molecule here. There's your oxygen, and here's the hydrogen here. Geometry is a little bit off here, but we could have then a hydrogen bond between, right, this hydrogen bond donor, which would be your oxygen, is the donor atom. This is the polar covalent bond, right? This is the hydrogen which is donated, and over here we have the oxygen right here, this oxygen, which acts as our hydrogen bond acceptor, and this would be the lone pair on that oxygen. Now, let's clear this. Actually, I don't want to clear this. Let's draw out what's happening with this OH group. So if we kind of draw that out, we have an OH. This is a polar covalent bond, and then up here we would have the hydrogen on the ring, and here we would have the rest of the ring. Now, we have on that oxygen non-bonding pairs of electrons. Each non-bonding pair of electrons can form a hydrogen bond with water, so we have potential for 2 hydrogen bonds here. This hydrogen is able to participate in a hydrogen bond as well, because here we have a polar covalent bond. And so in this case, the oxygen could act as a hydrogen bond donor as well. Remember that hydrogen bonds are very short in lifetime, and they form and reform and form and reform very, very quickly. And so there are here the potential for 3 different hydrogen bonds possible. We have a very similar situation going on over here with glycerol. So I'm going to start by looking at the molecule and defining where are the lone pair electrons. So we have here on that oxygen, on this oxygen, right, on this oxygen. And what I'm going to do is draw out the situation over here with this OH. So we have a C, right, a carbon. There's that CH2. I don't know why it's so hard to draw this out, but it is. And then we have an OH here. So here's those lone pair electrons on the oxygen. Each of those lone pair electrons is able to form a hydrogen bond with water, and in that case, the oxygen is acting as the hydrogen bond acceptor in that case. And then with this hydrogen over here, because it is participating in a polar covalent bond, the oxygen can act in another hydrogen bond as a hydrogen bond donor atom, because it's donating a hydrogen in that case. So again, we have the potential for 3 different types of hydrogen bonds around or involving this oxygen. So glycerol is going to be very highly soluble in water. That brings us then to our heptane, right? So we have 1, 2, 3, 4, 5, 6, 7, and there is an absence of polar groups here. This is a hydrocarbon, and it's very, very poorly soluble in water. And the reason, right, one of the reasons why it's poorly soluble in water is that it does not have the ability to form hydrogen bonds. There's not an appreciable enough difference in the electronegativity of carbon and hydrogen so that we have a polar covalent bond present. So heptane is a hydrophobic molecule, and it does not solubilize well in water. Let's cover the thermodynamic basis for why that is so. Here are the learning objectives, and I'll let you look through these on your own. Now, solubility of compounds that cannot hydrogen bond with water, the hydrophobic effect. So in the hydrophobic effect, what we're looking at is the lack of forming hydrogen bonds with solvent water. And because of this, when hydrophobic molecules insert into the material of water, we're forcing a highly ordered arrangement of water molecules. And because we're forcing this very highly ordered arrangement of water molecules, what we have is a severe decrease in randomness of the system. So we have a severe decrease in entropy. Let's take a look at our equation. So in this case, we have delta G equals delta H minus T delta S. The increase in enthalpy here is going to be slightly positive, so we have a slight positive delta H minus, and the temperature we'll say is constant, so we won't worry about it, T delta S, and our delta S is going to be very large negative. So again, our entropy is a measure of disorder in the system. And in just water by itself, we have this very random arrangement of water molecules, and they're happy to kind of be bouncing around and hydrogen bonding and, with all these different other water molecules. And it's a very chaotic type of arrangement here. So there's a high amount of randomness. When you insert something like a fatty acid, and that's what this would be, here's your aliphatic tail, and here's your polar head group. This is your carboxylic acid group. It's deprotonated, so it's really a carboxylate group. In this case, we're forming that highly ordered arrangement of water molecules, and this increase in order of the water molecules is causing the entropy to be a huge negative number. So what do we have up here in our equation? Then we have a slight positive delta H. So we have a positive value here minus a really big negative value here. And if you remember from just math, right? Minus a negative means plus a positive. And so in this case, our delta G ends up being positive. And because delta G is positive, it means that this is a thermodynamically unfavorable situation. And it is a non-spontaneous type of reaction. So in this case, what we have is the high degree of order in the water molecules being the main reason why this is a thermodynamically unfavorable situation. Well, how can we try to make this a little bit more favorable? We want to minimize the surface area here. So we want to arrange our hydrophobic molecules in such a way that we minimize the amount of surface area that's going to force order in the water molecule. So let's take a look here. Here you can see how the clustering of water molecules reduces the surface area exposed to water and reduces the number of water molecules that need to become ordered. So we have 3 fatty acids here, and they're packed together. And when those fatty acids are packed together, we have to cause this amount of water molecules to be ordered. If these fatty acids were by themselves in solution, we would increase the amount of surface area that would be exposed to the water, or we'd increase the number of water molecules that are exposed to the hydrophobic areas, and we'd increase the number of water molecules which need to be ordered. So that's a rough, approximation of the surface area now if these guys were not packed together. So we would have very great increase in hydrophobic surface area, which would cause the ordering of more water molecules, which would cause an even larger reduction in entropy. So it would be even more thermodynamically unfavorable. So by packing together the hydrophobic portions of these molecules, we reduce the surface area exposed to water. I should say we reduce the hydrophobic surface area exposed to water, and because we have a smaller hydrophobic surface area exposed to the water molecules, we have less water molecules that need to be ordered. Once we reach a certain concentration of amphipathic molecules in solution, and just to remind you, an amphipathic molecule is a molecule that has one portion of the molecule hydrophilic, so that would be the carboxylic acid groups here is hydrophilic, and one portion of the molecule hydrophobic. And so the hydrophobic portion of the molecule here would be the fatty tails, or the aliphatic tails. We can increase the solubility of these fatty acids if we arrange them in micelles. And so micelles are little spheres of fatty acids. And in this case, we have the hydrophobic aliphatic tails on the inside of this structure, and we have the hydrophilic carboxylic acid groups on the outside. And this is kind of the best of both worlds, and everybody's happy here because the solvent exposed groups are hydrophilic in nature, and we can have bonding with the water molecules, and they're very happy. So we're replacing the hydrogen bonds between water molecules with hydrogen bond interactions and electrostatic interactions between water molecules and carboxylate groups on the fatty acids. So in this case, we can replace So if we're looking at the bonds or the interactions, in the case below, we're able to replace the hydrogen bonds between water molecules, which are solvent-solvent interactions. We can trade those interactions, those bonding interactions, with water carboxylate group interactions. So these are solvent-solute interactions. And this is a much more thermodynamically favorable situation. We also have close packing of the fatty tails at the center, and those close packing associations would be as tight as possible to exclude water, and those fatty tails would exist at van der Waals distances. The atoms in neighboring fatty acid tails would exist at van der Waals distances from one another, which of course are extremely weak interactions. And so this close packing of the fatty tails helps to minimize the surface area of hydrophobic groups exposed to water, because with hydrophobic groups we can't substitute solvent-solute interactions in the place of solvent-solvent interactions. And so this is very thermodynamically unfavorable. So the concepts that were covered here and in the last slide pack are covered on the homework assignment, Solubility in Biological Systems, and Sapling Assignment 1.